Zambia has been experiencing unprecedented power shortages in recent years. The country has continued to record a significant power deficit due to persistent low water levels in reservoirs and rivers that drive the nation's main hydropower sources. Demand rose as more customers were connected to the grid, placing more strain on the limited power supplies. The solution to addressing the deficit lay in development of new power generation stations. In 2016, the government of Zambia took a bold step to commence the construction of the Kafue Gorge Lower Power Project. Once completed, this massive project would add 750 megawatts to the power pool. Works on the project have progressed steadily since commencement 4 years ago, and the main works are 84% complete.
As we sit now in January 2020, works have progressed extensively from when we began, and the Kafue Gorge Lower is now no longer in the middle of a bush. You can see construction works everywhere for the hydropower plant, as well as for infrastructure that will support the operations and maintenance of the power plant going into the operations phase. So the area is now opened up, and there are buildings, the houses, the powerhouse, the dam area, the intakes, all those are under construction, with some of the facilities already being completed.
The power stations are site-specific. You can't transplant what you have done here in one power station. The site would determine what type of dam you're going to construct, what type of machines you're going to put there. If you see sites like Iteshiteshi, for instance, what we call the head is very low, or the height of water, and therefore the best machine to use for such a site is called the Kaplan machine, where the head is what we refer to as medium head, meaning it's somewhere between 40 meters and 500 meters. Then you can use a Francis turbines.
The Kafue Gorge Lower Hydropower Project falls in the medium head category. A 130-meter dam wall is under construction to impound and create a water reservoir for power generation.
For the dam works, that is one of the major construction activities. Works initially required for us to divert the Kafue River to enable us to have a dry segment of the river for the construction of the dam. So the diversion was completed in 2017, and allowing us to excavate so that we can remove all the loose material and get to strong rock bed, so that then we build our dam, our RCC concrete dam on solid rock. And in terms of the RCC construction, we poured our first RCC concrete in June 2018, and as we sit now, we've done more than 95% of the RCC concrete already been put in place. On the right bank, we've reached the top elevation for the RCC concrete. In the middle, we have a spillway where if we have excess water, more than what we'll be able to use for generation, we'll have the spillway to discharge the excess water so that we can keep the integrity of the dam infrastructure.
The right non-overflow section on the right of the spillway, we are remaining with the 1.2 meters of RCC, roller compacted concrete, which we expect to finish tomorrow. And thereafter, we have 1 meter of CVC, conventional vibrated concrete, which we are to place. When we finish that, we'll start preparing laying of RCC on the left non-overflow section, which now has reached an elevation of 556 meters above sea level. That gives us a height of 105.5 meters from the foundation. That RCC we have to place for a height of 24 meters to reach the top, and then leave 1 meter of CVC, which we will do at the end. The middle section, which is the overflow section, the spillway section, works are also ongoing. We expect that all these works to do with the concrete have to be completed by end of March. Along the placement of concrete, CVC, we also plan to start the hydromechanical works, which are to do with the spillway gates. The gates are in, the embedments are in. Very soon we'll start putting the embedments. Once the embedments are done, then we do the gates.
The other construction works that we are undertaking, the intakes. At the intakes, we are constructing an intake tower, which is, once we impound the reservoir, it will be detached from the mainland, it will be islanded. So we've built up the intake tower. It has reached its 73-meter high tower.
The intake tower will house what we call the trash racks. There will be 5 trash racks, which will be used to screen off the trash during the operation of the power station. It will also house the bulkhead gates. There will be 2 bulkhead gates. Those gates will be used to stop the flow of water into the headrest tunnel. In the event that they would want to empty the tunnel. If you can see, there are reinforcements that are coming up. Those are for the bent frame, which will have the hoist system for the bulkhead gates. We've constructed the piers which will support the precast beams. During operations, the operation team needs to move from the other side on the bank all the way to the intake, and that would only be possible once we do the access bridge. Once all that is done, then we can commission the intake structure.
The intake structure channels water to the powerhouse through the headrest tunnel. Power tunnels shall direct water to each generating unit from the sage shaft. Construction of the power tunnels is being carried out meticulously. Each of the 5 power tunnels running over half a kilometer had to conform to very high standards. Sections of the tunnels are lined with concrete and some sections reinforced with steel lining to ensure that they withstand the high pressure of water passing through in the operation phase.
We have the horizontal part, which we call the low pressure part, and then vertical shafts and the lower horizontal, which is where we are. On average, each of the 5 power tunnel has a length of 647 meters. That's from the sage shaft up to the main inlet valve, the MIV, at the powerhouse. And of this 647 meters of length, we have about 312.5 meters of steel as the power tunnels are entering into the MIVs. The works are advanced. Power tunnel number 1, we've finished on the lower part, the steel lining and the concrete lining part. We have even started plugging what we call adit number 5, where I'm standing. This is an access tunnel which was used to access this area during excavation, as well as now as we do the concrete works and steel lining. Power tunnel number 2, concrete lining is finished on the upstream side of this adit. Steel lining is also finished. Power tunnel number 3, we have finished the steel lining. We are now doing the concrete lining. Power tunnel number 4, steel lining is ongoing, and power tunnel number 5, steel lining is also ongoing. So the power tunnel that we've now started closing up will be the first power tunnel to be commissioned in terms of having water go to the units, then followed by power tunnel number 3, just like that, until we reach the 5th tunnel.
The design of the power plant consists of 5 generator turbine units, each with the capacity to produce 150 megawatts of power. These power generating units are located in the powerhouse. Following the installation of water channels and auxiliary infrastructure to the units, work progressed to the assembly of the turbines.
The last time we showed you this area, this piece, which is called the head cover, was not in place. Then under the head cover we have the runner. It was also not in place. What we saw were guide vanes, which are these ones here. The guide vanes were all installed, and this was awaiting installation of the runner, and then this head cover and the shaft, which you see. So now the turbine area is all covered. We just have a few pieces which are coming up here. We have a regulating ring coming to sit here. That is what will regulate the opening and closing of these guide vanes. The movement of this regulating ring is provided by servo motors. There will be a servo motor here, another servo motor here, operated by high pressure oil to open and close the guide vanes or wicket gates.
The servo motors that operate the guide vanes are supplied with hydraulic oil from the hydraulic power unit at high pressure. The guide vanes regulate the flow of water to the generator units.
For us to be able to open and close, we are using hydraulic oil, which is coming from this station. Here we have a tank. This will have hydraulic oil. Then there are 2 AC-powered pumps, which are pumping the oil to the vessels here. Then there's a standby pump, which is DC. In case we lose AC power supply, because this is critical equipment, we still need to be able to run. So the oil comes into here. This will have a vessel which will have pressurized the oil, 160 bars. At the bottom we'll have oil, at the top we'll have nitrogen. So that nitrogen is coming from these cylinders here. So this is a nitrogen bank. Depending on the requirement here, we'll either push in nitrogen from the top or push in oil to maintain the required level of oil in this vessel. This is the turbine shaft. At the bottom, it's connected to the runner. And then at the top, it will be connected to the generator shaft. Then the generator shaft is what is connected to the rotor. So the movement down here from the runner is transmitted through this shaft to the rotor. Then as the rotor is rotating, we are generating power.
The generator units require cooling when they are operational. And the cooling system utilizes water drawn from the floor released from the generating units. This is water that flows back into the river downstream.
After we've used the water for generation, it goes into the draft tube where it's discharged into the river. So that's why we are pumping. We have pumps that are pumping on each machine. Now we have the valves installed on all the cooling water pipes. So these will enable us to isolate the cooling water system in case we need to do works on the cooling water system, or when we shut down the machine, in the sequence of shutting down, the cooling water also stops.
A backup cooling water supply is provided for in case of failure of the main supply pumps. This built-in redundancy is essential for uninterrupted functioning of the power generators. At the heart of the power generating mechanism are the stator and the rotor components. The assembly of these components is a painstaking process requiring nerve-wracking precision.
What we are seeing or happening here is the assembly of the stator. And it is in the stator that a voltage is induced. The stator comprises the stator frame, which is where I'm standing. The laminations have already been inserted or stuck. You can't see them for now because the assembly is complete. Then you've got the stator bars, which are these bars, or in simple terms, stator windings. And it is in these windings that we have an induced voltage due to electromagnetic induction. What is happening right now in this housing is completion of the assembly of the stator for unit number 1. Now we are just completing the circuit by interconnecting the 3 phases using our conductors. And once this has been completed, as you can see, it's almost complete, you end up with a star-connected stator. You have the phase terminals, which are my phase terminals over there, where once the induced voltage is connected, or that circuit is connected to the load, a current will flow in that circuit. And it is the product of the current and the voltage that gives you the power you always talk about. This is the rotor, or the rotating part of the generator. As the turbine spins, it will be rotating the rotor. And this rotor, in the rotor we inject a direct current. And that direct current will create a magnetic flux around the conductors. And it is that flux which, when it interfaces with the stator windings, we induce a voltage in the stator. But our main concern is the rotor construction which has taken place. This rotor assembly has already been completed. So for our machines at Kafue Gorge Lower, each rotor comprises of 24 poles. These are the poles I'm talking about, and the windings. So for unit 1, the rotor pole is already complete and ready to be lowered into the pit. As we assemble the stator or even the rotor, it is important that at any stage you carry out some tests. We do electrical tests and mechanical checks, because if you miss to check the integrity of your assembly, it can be a costly and time-consuming exercise.
What we are witnessing here today is the lifting of the rotor. The rotor is the heaviest component of the machine. We are talking about a total lifting of 360 tons. And then each crane is only 200 tons. So the 2 cranes put together, we've lifted the rotor into position. So this is a very critical lift because of the weight. 360 tons is not a small weight. And then as we bring it into the machine, the rotor is the inside part which rotates. Then around the rotor we have the stator, which is stationary. Then the clearance between the stator and the rotor is 32 millimeters. So it's a very tight clearance. So as we take it down, it is a slow process, because any movement of the rotor hitting onto the stator would cause damage to the stator. So with the rotor now lowered, we'll continue with the assembly of the other components below the rotor and also above the rotor.
After loading the rotor, that means all the equipment almost complete. The unit almost done. So anyhow, at the set, I will try my best to push the progress. Try our best to complete the unit. Then let Zambia get the power early.
Well, our generator units will be generating 13.8 kilovolts. This is a cell for transformer number 2. As you can see, the air coolers have already been assembled. The conservator tank has already been assembled. And most of the pipe work has already been done, and now we are waiting to assemble the low voltage bushings, which are these bushings we are seeing, and also the high voltage bushings or assembly, which will be in front, these will be behind. What you are seeing over there, my colleagues now preparing the oil filtering machine, because this transformer will be filled with oil. Now, we must make sure that the oil is clean and is of a certain quality. So to make sure that that is achieved, we need to filter and clean the oil to remove the moisture or any foreign particles, because those can cause short circuits in the transformers.
In all the construction works at Kafue Gorge Lower Power Project, stringent safety procedures have been put in place. These measures are aimed at preventing accidents that could cause harm to workers, damage to property, and disruption to works. Environment protection is also taken into account in all construction processes.
Before any work commences, we ensure that the contractor prepares a method statement, and in that method statement, we ensure that there is a risk assessment. We want to know the hazards that are associated with the works that we are carrying out, so that we protect our people, we protect the processes, we protect the environment as well as the property. This is very cardinal. And once the works are in progress, we ensure that we continue monitoring so that if there are deviations, we correct. When we talk of the environment, we ensure that we inform the regulatory agencies like ZEMA, we ensure that they come on board and they give expert advice on everything that we are doing. We do monitor the effluents that are coming from these construction sites. We monitor, we get samples and take to the laboratories so that the pollutants that are in those discharge is within the limits that are recommended by the regulatory agencies.
With the concerted effort of all, the Kafue Gorge Lower Power Project has achieved all the major milestones on the way to completion. It is anticipated that power will start flowing on schedule.
All I can say is to say we thank God that we're part of this and we're able to construct power plants, meaning that our engineers and everyone else who's involved, they're getting more knowledge. Thereby, once all this infrastructure is completed, they fully understand and they're able to maintain this with full knowledge because they participated in the construction of the same.